Okay, so again, last time in our last class, we talked about sequences. Okay, we talked about section 8.1, sequences. A sequence is a list of ordered numbers. Okay, it's numbers that follow a pattern. Okay, and the numbers go on and on and on following a pattern. And sequences can converge or diverge. A sequence converges if the numbers themselves approach a limit. Well, we also talked about series. So a series is when you add up all the terms of a sequence. And it turns out that a series will converge, series, which are sums, they can converge or diverge. A series, though, will converge if the partial sums of the series, or the sequence of partial sums of the series, converge. That's the formal definition of when a series converges. And we learned in our last class about some special series called geometric series. And geometric series have common ratios, and if the common ratio for a geometric series, if the absolute value of the common ratio is less than 1, that geometric series will converge. And not only that, there's a formula to find the sum. Right? So I want you to take a look at this series here. Do you think the series is a geometric series? Does the series appear to be a geometric series? What are your thoughts?
Yes, because of the exponent.
Very good, Maria. Maria's seeing that exponent down there, and that's. I mean, I want to be careful about saying, you know, like it's always the case that that would indicate a geometric series, but certainly it is intriguing, right? Now, let me just ask you this before we go to the solution here. Let me find my stylus. So if we were to write out some terms of the series, okay, and well, I want to just see here. Okay, what would the first term of the series be equal to?
1.
Good. Because the first term of the series is 1 over the square root of 2 raised to the 0th power, right? You start at n equals 0. So that first term is equal to 1. All right, what's the second term of the series going to equal? Well, the second term of the series, what's the value of n? Okay, that's right, Renaud. That would be 1 over square root of 2 to the first power. Okay, and this will just equal 1 over square root of 2. Okay, what's the third term of the series going to equal?
1/2.
Third term is going to, I'm sorry?
1/2.
1/2. Very good, Sophie. Because this is 1 over square root of 2 squared. Okay, and that root 2 times root 2 is 2. So that gets you 1/2. 1/2. And if we even go out another term, what would the next term be? 1 over
2 square root of 2.
2 square root of 2. Good. Good, Maria. So this series here is equal to 1 plus 1 over square root of 2 plus 1/2 plus 1 over 2 times the square root of 2. It's sort of a, it looks like maybe a little bit of a strange series, right? But to make the series a little more intuitive, it's often helpful to write out the first 4 or 5 terms of the series to help you identify the series, right? It gives you an intuitive feel for this series. Now, do you think it's possible to find some of this series? Based on the pattern here, what does the series appear to be? This series is a, what kind of series is it?
Geometric.
It's geometric. And Maria, what's the common ratio? Every geometric series has a common ratio.
1 over square root of 2.
That's right. Common ratio R is 1 over the square root of 2. Okay. So will this series converge? Given this common ratio? Leping says yes. That's right. Because 1 over square root of 2 is less than 1. And remember, in terms of common ratios, you know, common ratio says, like, if I take the second term and divide it by the first term, that's 1 over root 2 over 1. That just gives me 1 over root 2. If I were to take the third term of the series and divide it by the second term, okay, there the ratio would be 1/2 divided by 1 over square root of 2. Okay, and that's just going to be 1/2 times root 2 over 1. That's just going to be that's going to be 1 over root 2. So it's a common ratio. Any term of the series, if you divide by the term previous to it, the ratio will be 1 over root 2. Okay. Okay, so that being said, let's go ahead and find the sum. Let's go ahead and find the sum. So if we go to the solution here, what I do is, you know, just to kind of help you have a feel for the series, okay, when the series is written, well, first of all, 1 over root 2 to the n, I write it as 1/2 over root 2 to the nth power, because then that's going to be my common ratio, right? 1 over square root of 2 is the common ratio. And if I start the index at n equals 0, these here are the first 3 terms of the series. Okay, let me give you a moment to copy that. Sorry. Let me. I was had. Thank you. I did get that information. Thank you. I appreciate that, Nicole. So what I do here, again, is I just want to rewrite like this part here, 1 over the square root, 1 over the square root of 2 to the nth power. I write that as 1 over root 2 raised to the nth power. Okay, and I do that so I can get my common ratio R. The R is 1 over root 2. And what I do is, starting at n equals 0, okay, I write out the first 3 terms of the series. Okay, but there's a formula in section 8.2, hold on here, that says there's a formula in section 8.2 that says that if we write the geometric series this way, starting at n equals 1, okay, and any geometric series would take on this form that you see, this form here, the sum of that is going to be equal to a divided by 1 minus r. And of course, this is assuming that the absolute value of the common ratio is less than 1. Well, our common ratio is less than 1. And so what I can do, I mean, there are 2 ways to find the sum. Okay, if you want to like use the formula, to use the formula, you have to have your series start at n equals 1. So this series was given to you starting at n equals 0. Okay, but if I were to instead start the series at n equals 1, well, what gets changed is the power of n becomes the power n minus 1. See, if I change the starting index from n equals 0 to n equals 1, then I have to bring the power down 1. And that's why I subtract 1 from n. And it works because if you notice here on the right, what I've done is I've written out the first 3 terms of the series. Okay, starting at n equals 1. And if I like, you know, the 0 here, for instance, the 0 here, that's 1 minus 1. The 1 here is 2 minus 1, and so forth. So you see, you end up getting the same terms as you. So like you see, if you compare the two series that I wrote out here, whether I start the index at n equals 1 or I start the index at n equals 0, I'm generating the same series. This series here is equivalent to this series here. But writing a series in this form here, where n equals 1, allows me to utilize the formula in the book. It allows me to utilize it directly. I identify a as 1. This is a. I mean, there was nothing in front of 1 over root 2 to the n minus 1 power, but there was, right? A 1. A 1's there. And the common ratio is 1 over root 2. So hence, you get the sum. Now, 1 over 1 minus 1 over root 2, I'm going to write that as root 2 times root 2 over root 2 minus 1, simply by multiplying the top and the bottom here by root 2 over root 2. Okay, so that one way is to use the formula. One way to get the answer is to use the formula. Another way to get the answer is simply to do this. I know the first term, A is going to be my first term of the series. Okay, I know my first term's 1, and I know my common ratio is 1 over root 2. So sometimes students, they just they just, identify the series as a geometric series, and then they say, okay, well, the first term is 1. Common ratio is 1 over root 2. I can get the sum. So that's a second way. Okay? So don't let the fact that a geometric series starts at a different index at n equals 1, don't let that get you confused. The index could start with any number, really. And, we did one where n was equal to 0. Let's see. All right, hang on. So Renaud, you're wondering why sum 1 here is equal to sum 2. Am I getting your correct? Is that your question? Do I have it correct? Is that your question, Renaud? So, all right. Sum 1 and okay. Okay, so those are equal because, I generate the series for each one, and you can see they're equal. It's the same series. What Renaud's asking is, okay, how am I going from here, the original sum, why am I able to write it as this sum? Okay, so why is sum 1, or why is the first sum equal to the second sum? Okay, I can explain that. Let me show it to you here. So there's the sum, right? Original sum. Now, if I wanted to write the square root of 1, no, if I wanted to write the 1 here on top, could I write that 1 as 1 to the nth power? I mean, is 1 equal to 1 to the nth power? Yeah. Okay, well, so what is then 1 over n divided by root 2 over n? I can write that as 1 over root 2 to the nth power, right? I mean, a to the n over b to the n is equal to a over b to the nth power, right? So that's how I arrive. That's correct, Renaud. It's done because I mean, this is my common ratio here. Then, it helps me feel more comfortable about that being the common ratio. Okay, comfortable? Good, good. And these kind of manipulations are the kinds of manipulations that you'll have to do sometimes in the problems, because you always want to feel comfortable with the problem. Sophie, how did I get from the top middle to the one below it? Okay, hold on. How did I go from this sum here? Okay, I'll call that I'll call it sum 1, even though, it's I'm just doing that to be detailed, to give a little, so I can refer to it. Well, so you see what I did here. You see how the power, the index starts at n equals 0 in the first sum, but then in the second sum, the index starts at n equals 1. Are you seeing that, Sophie? Okay, well that means then I have to adjust my nth power to n minus first power so that both series start off with the same value. The first term of the series, the first term of that series 1, the first term of the series, when n equals 0, is 1 over root 2 to the 0th power. Okay, well, the second sum, the first term of the series, is also 1 over root 2 to the 0th power, because when n equals 1, okay, 1, when n is 1, 1 minus 1 is 0. See that? Because you're doing n minus 1. So you see, you got to ensure that both series start off with the same value. And then once you have that, establish that, you're good to go. All the remaining terms will all match like they do here. Listen, how many found that helpful that I wrote out those series? Okay, good, Sophie, good. Okay, excellent. Thank you, Jacob. Excellent. Excellent. Thank you, Nicole. All right, so we're basically now, okay, good. All right. So what do you notice? I mean, like looking at the terms of the series here. Okay, let's focus on the series in this form here. Here's some terms of the series. Here's some terms of the series. Okay, one moment. Okay, so here's some terms of the series. And the series has a finite sum. Absolutely amazing. You're adding an infinite number of numbers, and adding those infinite number of numbers gives you a finite sum. But for that to occur, what has to happen to the terms of the series? I mean, you look at the terms of the series. If we write, again, I'll write those terms. You know, we have 1 plus 1 over root 2 plus 1/2. Then we're going to have 1 over 2 root 2. And Renaud's noting the terms of the series have to get smaller, right? Terms of the series need to get smaller for the series to have any hopes of converging. Okay, but it turns out that just because the terms of the series are getting smaller and smaller and smaller, that doesn't mean the series is going to converge. The series could diverge. You can have terms of the series that get smaller and smaller and smaller and smaller, but yet the series equals infinity. How about that, huh? How about that? Let me show you why here. Let me go into the ebook. There's a series, it's actually in example 7 that I want to show you, called a harmonic series. Okay? This is not something that your average man or woman on the street would know, right? This is pretty special information here. Okay? I mean, you know, you got to have taken some math, advanced math to know this. All right, so let me go here to example 7. Yeah, this is what I want. Let me see, there was something in the chat here. Okay. All right, so yes. Yes, thank you, Iker and Nicole. I just didn't have a chance to reply back to you, but thank you for letting me know about the one student there. Well, actually, Renaud, a harmonic series is not a geometric series. So now we're talking about a different kind of series. Let me show you what a harmonic series is. Okay, so let me go to the okay, hold on here. All right. Is everybody seeing example 7 good from the ebook?
Yes.
Good. Excellent. Excellent. Thank you. Well, look at this series here. The series goes from n equals 1 to infinity of 1 over n, and they've written down the first 4 terms of that series. Okay, this harmonic series here. What's happening to the terms of the series? Terms are they getting larger or smaller? Yeah, they're getting smaller. However, you know what the sum of this series is? If you were to keep going with this series and keep adding and adding terms, do you know what the sum of that series is going to be? Infinity. It's going to be infinity. So, you know, I understand Jacob's thinking that it might be equal to 2 approximately, but it actually isn't. It's going to equal infinity because the harmonic series is divergent. See that? So this is worth, I think we need to look at the proof of this. How many of you are saying, no way, this is true? How many are very skeptical? All right, Tal can't believe it, and Michelle can't believe it, and Nathan's not buying it. Renaud's not. All right, well let's. I mean, this is absolutely amazing, right? These kind of things, and you don't see these kind of things till you get to maybe calculus 2. Then you start seeing interest like stuff like this, you know. Of course, the other math's good too. Nothing wrong with the other math, but this is fascinating. So here's what we're going to do. Here's what we're going to do. For this particular series, we're going to consider the partial sums. So the partial sums are S sub 2. That's the sum. Let me just see here. Hold on. Hold on. I don't want this to show. I don't want this to be, okay. I don't know why that's giving me blue. Don't give me blue. Please don't give me blue. Hold on here, everybody. I don't know why it's showing blue here. It's going a little bit crazy on me here. Okay. Come on, don't do that. Don't do that. Don't do that. Okay, so all right, now where's this proof come from? Where did they come up with this proof? Okay, well this proof was just over the years, mathematician came up with this proof, and actually they mentioned that this proof is based on due to the French scholar Nicole Oresme. Do you know when Nicole Oresme lived? He lived from year 1323 to year 1382. Okay, 1323 to year 1382. So this knowledge is about 650 years old, what you're seeing here. Okay? All right. Okay, what we're going to do is we're going to consider partial sums S2, S4, S8, S16, S sub 32. So S sub 2 is the sum of the first 2 terms, which is 1 plus a half. Okay, that's 3/2, right? S sub 4 would be the sum. So now I'm looking down here. I'm looking down here. I'm looking down in the box here. Okay, S sub 4 will be the sum of the first 4 terms, which is 1 plus 1/2 plus 1/3 plus 1/4. But they notice that 1/3 plus 1/4 is greater than 1/4 plus 1/4. So S sub 4 is greater than it's greater than 1 plus 2 over 2, because 1/2 and 1/4 and 1/4 makes 1, and 1 can be written as 2 over 2. Okay, and then they go to S sub 8. So it's like 2 squared is 4, 2 cubed is 8. They're doing partial sums by powers of 2. Okay, so S sub 8 is the sum of the first 8 terms of the series. Okay, but then what they do is they group the last 4 terms of the series. They group the last 4 of those terms, a 5th plus a 6th plus a 7th plus an 8th, and they're saying, well, okay, that would be greater, since that's greater than an 8th plus an 8th plus an 8th and an 8th. This means that this, let me just see if I can bring this up a little bit. This means that's going to be greater than 1 plus 1/2 plus 1/2 plus 1/2. So what they're doing is they're breaking the sum up into groups where each group would be greater than 1/2. Okay, that's what they're doing. So in other words, let's think of it like this. Let's write down what we have so far. Let me go to the whiteboard here. Go to the whiteboard. Okay, so for a harmonic series, okay, and the harmonic series is the series here. Okay, they establish that, okay, that I want to be careful how I write it here. Okay, so S sub 4, the sum of the first 4 terms of the series, is greater than 1 plus, I want to be careful how I phrase this. It's greater than 1 plus 2 times 1/2. Okay. Okay. And note that, you have S sub 4. 4 is equal to 2 squared. Okay, and I'm focusing on this 2 here. The eighth partial sum was greater than 1 plus 3 times 1/2. We'll note here that for the eighth partial sum, 8 is equal to 2 cubed. So we're trying to see if we can find a pattern here. Okay, now let's think about S sub 16. Okay, S sub 16, what do you think that's going to be greater than? If you add up the sum of the first 16 terms of the series, that's going to be greater than 1 plus what times 1/2? What do you think is going to go here? That's right, Nicole, 4. And they show that in the book. And I'll note here, okay, so there's the 4. We'll note that partial sum S sub 16, 16 is equal to 2 to what power? 2 to the 4th power. Okay. All right. So okay. What about the nth partial sum? The nth partial sum. Well, I should be careful here. I don't mean the nth partial sum. I mean the two to the nth power partial sum. This is the 2 to the nth power partial sum. What's the 2 to the nth power partial sum going to be greater than? So in other words, S to the, I want to try to make sure I'm writing it well. I don't like to, okay, let me write it again here. This is S sub 2 to the nth power. Now, that's going to be greater. That partial sum is going to be greater. Based on the pattern we're seeing, it's going to be greater than 1 plus what to the half power? N. That's right, Leping. Okay, so what we're seeing then is that, well, now the limit I want to make sure I'm writing it well. The limit as n goes to infinity of this 2 to the nth power partial sum, okay, would have to be greater. All the terms are positive, so it would have to be greater than the limit as n goes to infinity of 1 plus n over 2. What's that limit going to equal? So based on what we established here, okay, based on what we established there, right? The limit of the 2nth power partial sum would have to, as n goes to infinity, would have to be greater than the limit of 1 plus n over 2 as n goes to infinity. That equals infinity. Okay, so this implies this implies that the geometric series has to diverge. It has to diverge. Because whenever you know, whether, I mean, let's say this the right way. This here, this limit here, okay, this limit as n goes to infinity is the sum of the first 2n to the power terms, hang on, of the series. One just so the sum of the first 2n to the power terms of the series, okay, if we let n increase, we're you know, as you take more and more terms of the series, you're you know, that's like I want to say it the right way. I want to be very careful how I say it, but you're basically saying if the nth partial sum, remember what the definition of convergence or divergence of a series is. If the sequence of partial sums of a series converges, then the series converges. If the sequence of partial sums of the series diverges, then the series diverges. Well, we've established that our partial sums, the 2 to the nth power partial sums, okay, it's not every partial sum, but you know, it's a snapshot of partial sums, and they don't converge as n goes to infinity. So that means our series diverges. Our harmonic series diverges. And so now, anytime you see that, you know, the harmonic, anytime you have a harmonic series, you'll have divergence. Are there any questions on that? This reinforces the proof in example 7. But how many are feeling reasonably good about that now? How many? There were some people that said, no way that series can diverge. The terms are getting smaller and smaller and smaller, and yet the series diverges. Who's more of a believer now on that? Okay, Renat is, and hold on, we have some other folks here, and Jacob and Baraka. Yeah, I mean, basically the terms don't die down. They don't get small enough. They get smaller, but not at a fast enough rate for the series to converge. Okay. It's a little like, you know, remember the improper integrals. The improper integrals, if you have infinity, right, like an improper integral where the limits are 1 to infinity. Well, infinity, right, the area under the curve, under the function might get small, will get smaller and smaller, perhaps, as you go out to infinity. But if it doesn't get small enough at a fast enough rate, you know, the area accumulates. But if the area accumulates, if it doesn't, it accumulates. But if the rate at which the area accumulates is not fast, I want to say it the right way. I'm really trying to say it in a very nice way. The area accumulates in an improper integral, but the rate at how that area accumulates determines whether the interval the improper integral converges or diverges, right? So it's the same kind of principle here. Now, let me show you something else here in the whiteboard. Let me ask you another question. Okay, before we move on here. This is so important, this information that you're given here. Okay, does this series here diverge? And we can write out some terms of the series, you know, 1/2 plus, well, what would it be? First term is 1/2. What's the next term for this series?
1/3.
1/4, because you got the 2 there. So 2 times 2 is 4. What's the next term? 1/6. Next term, 1/8. What do you think about that series? Do you think that series converges or diverges? Renaud thinks diverges.
It's converged.
Nathan thinks diverges. Leping thinks, did you say converge, Leping?
Yes.
Okay, so I like it when we get a difference of opinion. Tall thinks converge. Okay. Well, it actually, and thank you everybody for your participation here. You know, maybe at some point I can have a thing where you know, where like I can do like a, I don't know, like a tally, you know, in the blackboard, you know, where like everybody can give thumbs up, thumbs down, and then I get a summary of the results, and I can say, you know, 10 people thought it converged, 9 people thought it diverged. But we won't worry about that now. The answer is yes, it diverges. Now, why is that? Why would that be? I'll show you why. See, this is a new kind of thinking here. Do you agree? I can write 1/2n times 1/n. I can do that, right? What can I do with the 1/2? What intuitively do I want to do with that 1/2 in the series? And I should put it in front, put it at right. Good. Good, Jacob. Good. I should say diverges here, right, for proper English. Hold on. Who chatted that? That's right, Sophie. That's right, Jacob. And I can do that, right, because we learn with series, you can move constants out in front. Okay, well, what kind of series is this series where n equals 1, n goes from 1 to infinity of 1/n? What kind of series is that again?
It's a harmonic.
Well, it's a harmonic, and our harmonic series diverges, right? So it equals infinity. This series equals infinity. That's sum. Well, what's 1/2 times infinity? It's still infinity, right? So the series diverges. Okay? Leping, are you comfortable with that? Tall, are you comfortable with that? Excellent, excellent. Leping,
Yeah.
how about you?
Yeah.
Okay.
I first thought it's too to the power of n. So I thought it's
Oh no,
geometry,
it's two
it's
times that.
geometry theory, so definitely it's converted. So it's my fault.
No problem, no problem. Okay, all right. So, all right, let's go ahead and look at a few more things here. I still want to do a few more examples. So I'm going to go back to the book. All right, it's hard to believe this has been not known for 650 years in the math community, but it has. It has. And not everything, not everything is, you're developing a new kind of intuition. I would phrase it that way. That gentleman, Nicole Oresme, who came up with that proof, he lived from 1323 to 1382. Okay, he was using some kind of intuition led him to that. Okay, and okay, now what about this series here? In example 8. The series where n equals 1 to infinity of n squared over 5n squared plus 4. They're saying that series diverges. So let's think intuitively. As n gets large, what do the terms in that series start behaving like? What do they start looking like? What fraction do the terms in that series start looking like when n is large? When n is large, is the 4 going to mean much? Is it going to matter much? No. So what is n squared over 5n squared equal to? So for n, when n is large, forget about the 4. I mean, you can't forget about it, but like it doesn't affect the value of the terms of the series. Okay, that's right, Jacob. 1/5. So this series, essentially, when n is large, when you're in the tail of the series, it's like you're adding up a fifth and a fifth and a fifth and a fifth and a fifth, and so forth. If you add up a bunch of fifths, what are you going to get? If somebody gave you infinity, right? If somebody gave you a fifth of a dollar, if somebody gave you 20 cents and did that every second, well, over time, you're going to be a rich person, right? Okay, it just builds. So, but they use something called the test for divergence. Okay, to show this, to be a little more formal, they use the test for divergence. Okay, and that says, basically, it says if the terms don't approach 0, the series definitely diverges, right? Okay, if the terms don't approach 0 of the series, it definitely diverges. And so if you formally look at the terms of this series here, okay, take the limit of the terms of the series, you're going to get a fifth, which isn't equal to 0. So the series diverges by the test for divergence. Okay. Okay, let me show you something else here. Let me show you another example. Let's look at example 4 here. One moment here. So I'm kind of going around a little bit here. Well, actually, let me go to example 6. Example 6 talks about a telescoping sum. So you see that series n equals 1 to infinity of 1 over n times n plus 1. That's not a harmonic series, okay? But what kind of series is it? Well, it turns out in the denominator, when you have a product of two like that, you have what's called, you have a telescoping sum. Okay, it's not a geometric series. So what they do is they say, okay, well, let's look at the partial sums of the series. Okay, let's look at the partial sums of the series. So if you add up the first n terms of the series, that's what your partial sum is going to look like in the box there. It's going to be 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over n times n plus 1. Okay? Now, the thing is, we would like to be able to simplify the 1 over I times I plus 1. We can simplify that. We can rewrite that. What approach did you learn that dealt with that kind of rational function, where you have to rewrite the rational function? Do you remember back from chapter 5? Sometimes to integrate a rational function, you had to rewrite the rational function using what approach? The method of, that's right, Nathan, partial fractions. So this nth partial sum, the 1 over I times I plus 1, I can rewrite that using the method of partial fractions. Partial fraction decomposition. Now they don't show the, hold on here. I don't know why it's showing that blue there. I don't want it to do that. Hold on. Maybe I can trick it. I'm trying to see if I can get the blue off, class. If I go fast enough, maybe. Well, all right. It's no big deal. We'll just leave it there. Hold on. There was something in the chat. Well, Sophie, if the term, so Sophie, yeah, let me get back to you on that, Sophie. I'll get back to you on that. Okay, I won't forget your question. So 1 over I times I plus 1 is equal to 1 over I minus 1 over I plus 1. So you would write 1 over I times I plus 1 as A over I plus B over I plus 1, and you would determine A equals 1 and B equals negative 1. Okay, well, if you do that, you can rewrite the nth partial sum like they show you here. If I can get it. I'm just trying to make it a little bigger for you. I don't know why it's not working. Hold on, everybody. Hold on. Let me go out, come back in here. One moment. We're going to get back to that question fast. We're looking at example 6 here in the ebook. Hold on. Let me share it here. Okay, I think that's good. So you see there how by using the partial fraction decomposition, you can rewrite this nth partial sum as the sum where I goes from 1 to n of 1 over I minus 1 over I plus 1. And then you can expand out the terms. And by expanding out the terms, you get cancellation. You get some cancellations, and you're left with the nth partial sum equaling 1 minus 1 over n plus 1. Well, are there any questions on that, what you're seeing there? Okay. Well, so what happens as n goes to infinity to the nth partial sum, the s sub n, the nth partial sum? Nth partial sum is 1 minus 1 over n plus 1. As n goes to infinity, what does the nth partial sum converge to? Converges to 1. That's right. And so, that's right, Nathan. And so this means then that because of that, because that's the case, this means then that our sum is equal to 1. So you see, it like a geometric series, you don't have to use this approach because there's a formula for the sum of a convergent geometric series. But for a telescoping series, you do have to use this approach. Okay. Are there any questions? I've tried, by the way, in the homework to include, I mean, I can't say every problem is going to have a help aid, but I try to, when I see problems with help aids, I definitely like to assign them, you know, because, hold on, there was a question here. Telescoping, what makes it telescoping, Nathan? Well, a telescope, it's like, hold on here. So there, the nth partial sum, like, you know how a telescope stretches out? I mean, at least I think people know what a telescope is these days. I'm thinking of like the sailors when they used a telescope. You know, they would have a telescope that expanded out. How many have seen that? You know. Okay, yeah. So you can expand the telescope out. It's a telescope. This series, you can write the series out in that special way, and then you can see what terms are going to cancel out, and then you're able to get an expression for the nth partial sum of the series. Good, Nathan? Excellent. Oh, and now, Sophie, your question, hold on, the question, Sophie had a question. Sophie says, why don't you mention that if the terms don't approach 0, it definitely diverges? Well, yeah, if the terms don't approach 0 of your series, the series will diverge. I got to be a little careful on this. Under normal circumstances, if the terms don't approach 0, well, no, if the terms don't approach 0 in your series, if they don't get smaller, the series will diverge. But the fact is, you can have a series, like a harmonic series, where the terms approach 0 in the series, but yet the series diverges, you see. So just because the terms are getting smaller and smaller in a series doesn't mean that that series converges. It could diverge, as in the harmonic series. It really depends on the rate at which the terms are approaching 0 to determine convergence or divergence. Just like with an improper integral, the rate at which the area is getting smaller and smaller out in the tail, you know, under the curve. that determines divergence or convergence. Okay, hold on here. Okay, good, Sophie. Excellent, excellent. Okay, well, yeah, and in terms of the telescoping series, they put enough terms in there so that you can hopefully determine the pattern. Basically, and that's what they're doing. Let me show one more one here, because I want to give you some time to work on this. Maybe I'll show a few more examples here. Let's look at example 3. Okay, example 3, they want to know if that series is convergent or divergent. So the series is n equals 1. Okay, hold on. Series goes from n equals 1 to infinity, 2 to the 2nth power times 3 to the 1 minus nth power. Okay, so what they do is in the solution here, they try to rewrite the series as a geometric series. Okay, so take a look at what they're doing in the box there, and I want to see if this makes sense to you. Maybe what I can do is write it out here a little bit in the recording, just to let me go to the whiteboard. So example 3. I mean, everything's fine, but I just feel like doing it on the whiteboard. So example 3 from the book. Example 3. Have this series here. Okay. Sorry, that should be 1 minus n here. Okay, now this series, when you see like the exponents, what comes to your mind? What kind of series comes to your mind that you hope that this example 3 series will be? I see to the 2nth power. That's right, Jacob, a geometric series. So hopefully I can rewrite this and come up with a geometric series. Now geometric series, in my mind, I'm thinking, okay. Standard form of a geometric series is going to be something of this form. Okay, now I got n equals 1, so I'm happy there. Okay. But I'd like to get the nth power out. So I'll write 2 to the 2nth power as 2 squared to the nth power. And I'll write the 3, and I'm not looking in the book how they're doing. I'm doing it my way. I'm going to write 3 to the 1 minus nth power as 3 to the 1th times 3 to the negative nth power. Okay. This here, incidentally, now is 4 to the nth power. 2 squared is 4. So what I'm going to do here is I'm going to just leave the 3 here. And I got 4 to the nth over 3 to the nth. Because 3 to the negative nth is like 1 over 3 to the positive nth. Okay. Well, okay. Are there any questions so far? Four over n, 4 to the nth power times 3 to the nth power is 4 over 3 to the nth power. Okay, well, 4 over 3 to the nth power I can write as 4 over 3 to the first power times 4 over 3 to the n minus first power. See, I want to get the n minus 1 power in there. And then 3 times 4/3 is 4. So this is different than the way the book did it. But this series can be written then as 4 times 4/3. Let's try to make that look good. Such beautiful stuff and so useful. So useful. This is what I got. What's A equal to? What's A equal to? This is in the standard form I want. Good, A equals 4. So here's A. And what's R equal to? What's the common ratio going to equal? Good, 4/3. This is R. Sophie says, how did I get from the 3rd row to the 4th row? 3rd row to the 4th row. Okay, so if I have like A to the nth power, well, maybe I don't want to use A because, you know, I don't want to get the variables mixed up. But if I had like D to the nth power, is that equal to D to the nth power minus 1 times D to the first power? Is that okay? You're good with that, Sophie. All right, well, all I did was I wrote 4/3 to the nth power. Think of 4/3 as D. I wrote it as 4/3 to the first power times 4/3 to the n minus first power. Yeah. Good, good, excellent. Okay. Well, so should I go ahead and try to get the sum of this series? Here's my series. Here it is. Does that geometric series converge? No. No, because the common ratio of 4/3, the absolute value of that is 4/3. That's greater than 1. So this series diverges. And in WebAssign, I think when you put diverges, you have to use capitals. Usually it'll tell you. But yeah, that series diverges. Okay. Let me show you one more example here. Are there any questions on this? All right, let me go to example 4. Then let me go to example 4. So I was debating whether to, I mean, sometimes naturally you have to look at examples yourself, but incidentally, on that problem that we just did, okay, they say, well, the first 3 terms of the series are 4 plus 16 thirds plus 64 ninths. You can see the terms are getting bigger, right? So that series is going to equal infinity, that sum. That's going to diverge. Okay, how many of you knew that you could express a repeating decimal as a rational number? Okay, what's a good example of that? Okay, Sean and Renaud know that. What's a good example of that? That's right, Renaud. 1/3. 1/3 is 0.33333333. So, that's an easy one, right? But what if you had something like 2.317, where the 1/7's repeating? Well, you can use convergent geometric series to help you. You could use it to help you. Because the 2.317171717, that repeating thing, well, you can write that as 2.3, that repeating decimal, you can write as 2.3 plus 17 over 10 thirds, plus 17 over 10 fifths, plus 17 over 10 sevenths, and so forth. Do you see that? Maybe I can make it a little more clear here. Let me go to the whiteboard. Hold on. How many find the trips to the whiteboard helpful? Are these helpful, our little trips to the whiteboard? Okay, wow. I'm getting a lot of replies. Okay. Thank you. All right. Very good. Very good. And this is why I like recordings as opposed to like handing out documents, because those aren't in the recording. The recording's the best, Recording's the best. Okay, so let me just, this is example 4 that we're looking at here. I just want to justify the comment that they made there. Okay, so this would be 2.3 plus 0.017 plus 0. So like, the 1/7, the 7 is in the thousandth decimal place. So, there's the 7 there. The next 7 is in the the 100,000th decimal place. So the next 7 is in the 10 millionth decimal place. 3, 4, 5, 1, 7. And you can keep going with this. So this is how you get 2.3 plus 17 over 10 thirds, because 0.017 is equal to 17 thousandths. 10 to the third is 1,000, right? And then 0.00017, that's equal to 1700 thousandths. Well, that's 17 over 10 to the fifth. I mean, if you just say it, 0.00017, that's 1700 thousandths. Well, that's 17 over 10 to the 5th power. And then, you know, finally, this is 17 10 millionths. So that's going to be 17 over 10 to the 7th power. See what they're doing there? And so what happens is, as you keep going, this portion here, this portion is what kind of series? What kind of series is that? (17 over 10 cubed plus 17 over 10 to the 5th plus 17 over 10 to the 7th plus, you know, what kind of series is that? Okay, Nathan says a geometric series. Sophie says geometric. All right, if it's a geometric series, can you tell me what the common ratio is? Well, the first term, of course, first term is 17 over 10 cubed, right? We know that's the first term. But hold on, what did you say, Tal? What's the common ratio?
1 over 10 squared.
Good, good. Common ratio is, let me put it in red here, is 1 over 10 squared. And that's less than 1. So this is going to be a convergent. This here is a convergent geometric series. And we can find its sum. So let me go back to the book then, if we're good. Are there any questions on this? All right, well then if I go back to the book to finish up this example 4, so there's the confirmed first term of the geometric series, common ratio, and they're able to write that, hold on, I guess I don't, well, yeah, that's fine. They're able to write the repeating decimal as a rational number. The 17 over 10 cubed divided by 1 minus 1 over 10 squared, that's the A over 1 minus R. That's the sum of the geometric series. Let me see on that. Hold on. Nathan's asking, why not let A be 17 and R be 1 over 10 to the 5th? Well, the thing is, if you look above, Nathan, you have 17 over 10 cubed as your first term of the series. So you can't separate the 7. The A has to be 17 over 10 cubed. Now, if you factored out a 17 from all those terms, you could have this. You could have this. You could have this. You could have 7. I want to say it the right way. The 17 over 10 cubed plus 17 over 10 to the 5th plus 17 over 10 to the 7th, and so forth. You could factor 17 out of everything, And then this series here would have the sum, well, I mean, here's your A right here, right? So that's going to be 1 over 10 cubed divided by 1 minus 1 over 10 squared. Okay, that's the A over 1 minus R. And if you multiply that then by 17, you'll get the same answer the book did. How many like that better, factoring that 17 out? I kind of like Nathan's idea there. I mean, I think that's what he's thinking about. Nathan, are you good with that? Good, good. Let me see. Marcus says, in this type of equation, would A generally be the first term? Yes, Marcus, it would. In a geometric series, the A is the first term of the series. Yes, that's correct. Okay, great. You're welcome. All right, now what I'm going to do is I'm going to give you half an hour here to work on. I'm going to make section 8.3 available. I'm going to give you half an hour to work on that because that is, I'm sorry, 8.2, because that section 8.2 is due this Thursday. There are 27 problems in that section. So, you know, I want to give you a little time to work on it. You know, take a little break. Hold on a minute. Are there any questions before I stop the recording?